Okay, so so you guys are probably in the throes of demoing your project reports and submitting your final homework. So if you have any questions about any of that, let me know right now before I get started. We are roughly one lecture behind, which means that I might not be able to cover all of the material that I had set out to at the start of the semester, which is totally fine. And based on how much I'm able to cover, I will, over the next two lectures, so today and Wednesday, I'll let you know how much I've covered, and then I'll let you know what doesn't need to be read for the second midterm. Okay? Any questions about anything about the second midterm? So you should have seen a note on Piazza that says that the second midterm will be held in class next week on Monday. It'll be in the usual class slot, but we require you to come 10 minutes early, okay, just so that we can get you settled in. And hopefully that's not too much of a burden because you're anyway used to coming at 8 a.m., or at least some of you. All right, so any questions before I get started? All right, so we are switching gears from query optimization to a new topic, which is transaction management. This is an equally important topic. So there are two aspects to this topic that we are going to be covering. The first is the notion of transactions themselves. It's a super important concept, and the notion of recovery. Okay, so how do you recover from failures? So far we've been talking about how do you sort of query a database. We also talked about how do you modify a database, right? So you can use commands like update set where as one mechanism to modify the data inherent in a database. And we've assumed that these update set where statements are executed one at a time. Okay, so in some sense, implicitly, we've been assuming that when there are multiple clients trying to modify the database, these sort of modifications happen in sequence such that one of them completes their modification before the other one touches the database, does their modification, and so on. So implicitly, and we want that behavior, right? So if you're developing banking software, flight software, even, I don't know, social network software, you want your updates to happen in such a manner such that your changes don't interfere with someone else's changes. Okay, so so far we've basically assumed that each operation is executed one at a time, and therefore one operation executes, perhaps changes the database state, and then the next operation executes. Okay, so this property of each operation not affecting other operations is a property that is known as isolation. This is one of the desired properties that is provided by the database. The second assumption that we made so far is that each operation is executed in entirety or not executed at all. Okay? And we'll talk about why that's important. That notion or that guarantee that the database provides is a notion or guarantee of atomicity, the fact that each operation is atomic. Okay? And this is just what you need when you're modifying the database. You don't want to end up in a state where some stuff is incorrect. You don't want to end up in a state where stuff is inconsistent. Okay, so that's just what we need from the database. So if these assumptions are violated, then there are funky things can happen to your data, right? So for instance, if you have multiple operations that are accessing the same table simultaneously, they could end up messing the data in a way that is not intended, okay, in a way that you don't really intend. Similarly, if you have for instance, a crash that happens in the system in the middle of an operation, then you could have complications, right? So let's say you were doing an update operation, and half of the tuples have been updated, but the other half haven't been updated, and the system crashes, then half of the tuples reflect the update, half doesn't, and you don't want that happening, right? So these are sort of complications that you want to avoid when you're performing updates to a database. Remember that when issuing queries, this is not as much of a problem. When you're issuing simple select from where, it doesn't matter as much because you're not touching the database. These considerations arise and are important when you're touching the database and making modifications. Okay. So, so a database system must not crash. It can't be allowed to be inconsistent. This is a saying, a database that's 1% inaccurate is 100% unusable. This is true. If a banking software is 1% inaccurate, it's 100% unusable, right? You don't want a database system that is powering a banking application or a flight application to be inaccurate at any point, okay? So you don't want the system to lose data. Everything that you do should be reflected in your database, and you don't want a database system to become unavailable at any point. Okay, so we're going to zoom in and focus on one specific aspect of this. Before that, I'm going to introduce the notion of transactions, and to motivate that, I'll do a couple of examples. So the first example is that of flight seat selection. So let's say I have some program that has two statements. The first statement is a select from where, and the second statement is update set where. Okay, so I'm first checking if the seat is available. If the seat is available, then I'm going to change its availability to occupied. So basically, I'm giving someone a flight seat. Okay, let's say there are two individuals who are both running this program at the same time. So you have, let me move this here. You have one run corresponding to customer 1 and another run corresponding to customer 2. And so let's say customer 1 looked up, said, hey, I want a flight seat, and turns out there is this particular flight seat, which is a great seat. It's an exit row, aisle seat. And so that customer says, yes, I want that, right? The same time, customer 2 comes in. So the customer 2's program is running. Customer 2's program also looks at the same flight map and then picks the exact same seat. Okay? Now, after that, let's say the second statement of customer 1's program runs and then changes the availability of that exit row aisle seat to occupied. And then customer 2's program once again changes it to occupied. So basically, in some sense, both of these customers have been reserved the exact same seat. You don't want that to happen, right? So in some sense, what you want to happen ideally is for A1 and B1 to happen before A2 and B2, or A2 and B2 to happen before A1 and B1, right? This form of interleaved execution will lead to issues because you have an overbooking problem with multiple individuals assigned the same seat, and you know how well that went out for United, right? So, so you don't want that to happen, right? So you don't want the same seat to be assigned to two individuals, okay? Okay, so you have two executions of the same seat, or two executions of the same update set where statement leading to a seat being double booked. You don't want that to happen. Okay, so the lesson from this example is that what we need to do is to group these two statements, the A and the B statement, into a single grouped statement, and have those execute as a unit such that either both of them execute or neither of them execute, right? So group the select from where, which retrieves seat availability, and the update set where, which reserved a seat, into one transaction, right? So in a transaction, it's a sequence of statements which is considered to be a unit of operation in a database. This is where I'm defining the notion of a transaction. A transaction is a sequence of statements that are doing multiple operations to a database that are considered one unit. You want them to be executed all at once, and you want them to be executed without interference from other transactions. Okay, so basically you want either user 1's transaction to execute first, and then user 2's transaction, or the other way around, but you don't want them to execute in a way that interferes with each other. This property is known as serializability. And the reason why it's called as serializability is because it's happening in serial order or in sequence, and therefore it is that's why it's termed serializable. Okay, so overall, like once again, as a reminder, a transaction is a collection of statements that need to be executed together. Serializability is a property of transactions that guarantees that these transactions are executed in a manner that don't interfere with each other. You have all of one transaction executing before or after another transaction executing. Okay, so let's look at another example. So let's say this is a bank transfer between maybe one account to another account. So this is one user who's interacting with the database, and this user first checks if this account has greater than $100, then reduces this balance by $100, and then increases the balance of another account by $100. So this user is simply transferring money from one account to another account. Okay, so what happens if there's a crash after this step, right? So in this case, the database system has basically recorded the first update, but has not recorded the second update. So the money has reduced from one account, but has not reappeared in another account. Now, this is an issue. Customers don't like this, right? You don't want your money to magically disappear. Right? So this is not a scenario that customers would want. So your database system has to be resilient to such failures. You need to be able to recover from such system crashes. Okay, so in some sense what we want is the other property of transactions, which is known as atomicity. You want statements 2 and 3 to be executed as one unit. You want it to be executed both or none at all, right? So you don't want money to disappear from one account and not reappear in another account. You're okay with money not moving at all, because that's just saying, hey, look, nothing has happened. You may need to rerun your transaction. But if money has disappeared, not reappeared, that's not a scenario I want to happen. Okay? All right. So basically, you either want both of them to execute or neither of them to execute, right? Okay. So this is the second property of a transaction that we want, which is that they are atomic. They, either all of their changes should be reflected, or none of them should be reflected. Okay. So this is how you declare transactions in SQL. You say you have a statement which is called start transaction, and then you have a bunch of SQL statements, and then you say commit. Okay. Now these statements 1 through n are now grouped together. They form an atomic unit. They are executed either all of them or none of them, and they are serialized, which means that you have one transaction executing, and then another transaction, then another transaction, and not in a weird interleaved fashion. Actually, in practice, it may, the database system might actually interleave these transactions, but does so in a manner that is not, does not cause any errors to the database. So it may actually end up interleaving the transaction, but that execution order will be equivalent to some serial execution order. Okay, so it does so in a manner that there is no interference between the transactions. But that's not a topic we're going to be covering in the course, so I won't dwell on it. Overall, you can assume that database systems will take these transactions, which are declared using this syntax, and then treat them as an atomic unit. So either all of them execute or none of them execute, and that they are serialized. Okay, so basically, essentially, the transactions don't interfere with each other. Their effects aren't felt by other transactions. Either they are felt in a way that all of transaction 1's updates are done, and then transaction 2's updates are done, not in a mixed manner. Okay, so it's not in an interleaved fashion. Okay, so in addition to this, yes? Yeah. Yeah. So you can assume that they do overlap, but the database system will guarantee that there is no interference. So for instance, let's say you have two transactions. Transaction 1 is updating A and B. Transaction 2 is updating C and D. They can be executed in an interleaved manner. It doesn't affect things, right? So at least that intuition should be obvious, yeah, right? So, but if there are two transactions that are both updating the same flight seat, you don't want that happening. Any questions about this stuff? Okay, so the other syntax here to note is the syntax of rollback. So what if midway through a transaction you decide that you don't want to go through with it, right? You've gone and you've read the flight, you've looked through the flight seat selection, you've gone and selected it, and you finally realize that the price is too much, right? At that point, you want to say, don't execute any of this, right? Don't persist any of the changes that I've made. For such a scenario, what you want to do is to roll back this transaction. So so you could have a statement here that says, if you've noted something that tells us not to go to statement I+1, you can roll back. Otherwise, if the customer tells you to do something, you can roll back. If you have a rollback operation, what that means is, if that if condition ends up being true, then essentially the effects of the previous statements are all eliminated, and this transaction effectively does not execute, right? So this transaction is what is known as aborted. So if the transaction ends up being executed, you call that transaction committed. Okay? So, yes, question? Okay. So you can have any number of these if clauses or if statements with rollback if you want to check for various conditions during this transaction. Okay? Oops. All right. So a rollback causes a transaction to abort. The effects of statements 1 through I will not be present after the transaction completes. So that's the syntax part. Now let's talk about how this is actually managed by the database. So this is done by this part of the database internal, so the database system, which is called the transaction manager. Transaction manager's job is to execute transactions as expected. There are three uses or purposes of a transaction manager. The first purpose is to talk to a so-called log manager that ensures that the steps that are taken by a transaction are logged. Okay? And the log is, as we will see later, is a mechanism that allows a database system to recover from a system crash. Okay? So you have system crashes. The log allows you to recover from such a crash. The second purpose, so the first purpose is to talk to the log manager. The second purpose is to recover from a crash using these logs. Okay, and the third purpose is to execute these transactions in a serializable manner. So these transactions execute in parallel in a way that don't interfere with each other. Okay, so so the first two purposes are what I am calling logging and recovery here. The third purpose, which is to ensure that these transactions don't interfere with each other, is concurrency control. Okay, so logging and recovery basically is one function of the database which ensures that everything gets logged, all the changes that you're making gets logged, and then uses those logs to restore a database to a state before the to a consistent state, to a state where either a bunch of transactions have been executed completely or have been aborted. There are no transactions that are partially executed. Okay, so that's the first two purposes are handled by logging and recovery. The third purpose, which is to ensure that transactions don't interfere with each other, this is the role of concurrency control. You may have seen concurrency control in other other computer science classes. For instance, if you've taken an operating systems class, you may have seen concurrency control, especially when you're studying locks and synchronization and mutexes. So this is not going to be covered in this class, but this is an important database systems topic as well. So if you're interested, you can consider taking the advanced data management class, which has more on this stuff. Okay, so that's 511. Okay, so let's talk about what does logging target. So since we are focusing on logging and recovery, what does logging and recovery target, and what are the sorts of errors that it's actually recovering from? So firstly, what can go wrong, right? So the first kind of thing that can go wrong to a database is wrong data entry, right? So this is something that you can either prevent by having constraints in a database, or you can do some form of data cleaning. You can look for values that are potentially erroneous. So if you have a -1 where someone's age should be, that's probably a wrong value. You don't want to have that. So these are things that you typically check even before you enter the data in a database, or once you've entered it, you clean it up via constraints or triggers. So this is not the purpose of recovery. The second thing that could go wrong is disk crashes, right? So you could have all of your data that you've stored on your disk just disappear, right? And the way you handle this is to either use a redundant array of disks, so RAID, or you periodically take a backup or an archive of the data. So these are, again, not the purpose of recovery. So this is something that can be periodically done or is automatically done at all times via a RAID system. So again, this is not the purpose of recovery as we're going to be talking about. Then you have stuff that is even worse, right? You could have fire, theft, bankruptcy, and essentially you have good luck with that, right? I mean, those are things that you can't really handle with any database system functionality, right? So you can buy insurance and change profession, but good luck with those, right? So those are not things that we can handle. So what we are handling are system failures. So this is by far the most common kind of thing that goes wrong. So this is either a power failure or some exception due to the system. The database system crashes. So basically, whatever is in memory disappears. Whatever is on disk still stays. But at the same time, there are some transactions that are partially executed. So their effects may not have been felt on disk, right? So that's where you need to recover from. Okay, so this is what we're going to be focusing on, system failures. So what do we do for system failures? Okay, so like I said, each transaction maintains some kind of internal state. This is usually in memory. And this internal state, as soon as the system crashes, all of this disappears, right? Right now, memory is not persistent, right? As of now, RAM is not persistent. Therefore, whatever you've stored in memory, as soon as you switch off the computer, it disappears. So you have no idea which parts of your transaction have executed and which parts haven't executed. So the remedy for this is to use a log. A log, like the name suggests, is a file that records every single action that is taken by the transaction. Okay, it's just recording what is going on in the transaction and across all transactions. So in order to describe what a log does and how it affects recovery, we'll talk about a simple sort of language that a logging system would use to record what the transactions do. Okay, so to talk about this language, we first need the notion of elements that the language touches. So these elements are what compose a database. So an element is typically one block, but it can be even smaller. It can be one record, or it can be even larger at the level of a relation. Okay, so the updates that we are recording are going to be at the level of these elements. So you say this element has been updated from this value to this value. For our purposes, we are not going to be worrying as much about whether it's a block, whether it's a tuple, whether it's a relation, whether it's a record. We're not going to be worrying about those distinctions. I just want you to get the flavor of what the database system does. So we're going to be operating on very simple variables, as opposed with variables being undefined. They can be blocks, they can be tuples, they can be values, they can be relations. But we're going to be operating on variables. So I'll say, hey, value A has been changed from 10 to 15, right? So I'm not going to tell you what that value A is. It could be a tuple, it could be a record, it could be a tuple, it could be a value, it could be a block, it could be a relation. Okay, so we're not going to worry about that as much as the semantics of what that means and how we'll recover from that. Irrespective of whether it's a tuple, a block, or a value, it's going to be the same semantics. Okay, it's going to look roughly the same, so that's why we're not going to worry about it as much. I just want you to understand the concepts behind recovery. So each transaction reads and writes some elements, the elements being undefined, and there are three spaces that can store these elements. The first space is the disk block, of course, so that's where your data typically resides in. And then you're all familiar with the main memory buffers, so you bring data from disk to these main memory buffers. So that's another place that these elements could reside in, right? So this is managed by the buffer manager. And then finally, you can have some local memory of the transaction, which is typically much smaller than the main memory buffers, but it can record some temporary variables, right? So you could, for instance, if you have a C++ program or a JavaScript program that is doing your flight update, it might have some variable called price, which is read from the database. From the database, it's loaded into your main memory buffer. From the main memory buffer, it's loaded into some variable which is called price, right? So this would be what I would call the local memory of your transaction. Okay, so this is managed by the transaction manager. So let's talk about operations that these transactions can perform. So the first operation is an input operation. So the input operation reads element X from disk into the main memory buffer. Okay, so this is input. Then the operation read X comma T copies something from the main memory buffer to a local variable T. Okay, so this is read. Okay, and then you have write. So write would be writing something from local variable T to element X in main memory. And then finally, output would output from the main memory buffer to disk. Okay, so in some sense, for query processing and query optimization, we focus primarily on these two. But of course, if you have multiple steps in your transaction, you may need to have local variables as well, right? That seems like it would make sense. So for instance, if your customer has said, or if your program says, if you have enough money in your bank account, then you are allowed to make this credit card payment, right? So the checking whether you have enough money would be done using local variables that would store values temporarily, and then let's say your Java program uses those local variables, checks whether there's enough money to make to proceed on some payment, and then it would perform the update. Okay, so so far we've been focusing on these two, at least in the query optimization and query processing sections, but it seems like it's fairly intuitive why you might want to have local variables, especially when you have multiple statements with stuff that you may need to record in between, right? Any questions about this stuff? Okay. So let's consider a simple example and walk through what these operations may result in. So let's say you have two elements A and B, and the database system is always trying to ensure that A and B are always equal. Okay, so that's the guarantee that the database system is trying to ensure. So you have one transaction which is doubling A and then doubling B, right? You don't want the transactions effects only on A to be present without the effects on B to be present, for example, right? So if the transaction starts in a state where A is equal to B and executes without system failure or without interference from other transactions, then obviously A will be equal to B at the end of the transaction's execution, right? Because you've doubled both A and B. Yes? Okay. So here are how one execution of this transaction T might look like. So let's say you have the values 8 and 8 for A and B on disk. Again, these are elements being undefined. It could be records, it could be values, it could be values meaning values of a certain attribute, or it could be blocks or relations, okay? So the action that's being taken here is you've said input A, so basically you're reading from disk to memory, and then read A comma T, so you're moving or you're copying the value from memory to the variable T. You're doubling T here from 8 to 16, and then you're writing 16 to the main memory buffer location for A. Then you're inputting B, so from disk to memory, you're reading B from memory to the temporary variable, you're doubling it, then you're writing it to the, sorry, not here, then you're writing it to the main memory location for B, and then you have the two steps of output here, so you're outputting from the main memory location of A to disk and from the main memory location of B to disk. Okay, so this is the step-by-step execution of this simple program which was A is equal to A times 2 and B is equal to B times 2. Right? So these are the internal operations that would be performed for executing this transaction. Yes? Internally, can output A and output B be done at the same time? Okay, so this is a more of a it's a bit of a complex question. It depends on the scenario, but typically not, because if you're doing I/O, so if you're writing out something to disk, even though there can be multiple things that are written out to disk at the same time, there's always a case where you have already too much stuff to write out. So let's say you're updating 100 elements and then writing all of them out to disk. You may not have that many disk heads such that you can write all of them out at the same time. So inevitably you'll run into the problem of sequential execution. You'll have to write out some stuff first before writing out other stuff. So that is really the problem. Because you are writing out stuff in sequence, you may have written out A and then crash. Then you wouldn't have written out B, and then you're in a soup. Okay, so here, basically, up until this point, you're good, right? Up until this point, you've not changed any of the data in your database. You have 8 and 8 on both A and B, so you're okay. So up until this point, you're okay, right? Your database is consistent. If you crash after doing output A, then you're in bad shape, right? This is because you've modified A on disk, but you've not modified B on disk. So you have a partial transactions effects on the database. You don't want that to happen. Once you've edited B on disk, starting from this point, you're in good shape again, right? Because both A and B have been updated. So this is the one case that we want to avoid. We want to avoid the scenario where you've updated A but not updated B, right? You either don't want to update either of the two, or you want to have updated both of the two, right? So that's really what we want, and logging will help us achieve that. Any questions about this? Okay. So like I said, if the crash happens before output A, then no harm done. The database stays in the consistent state. the crash happens after output B, then once again you're okay because the database is in a new consistent state. If the crash happens after output A but before output B, then you're in an inconsistent state. So this is a case that we want to catch and recover from. So recovery has to ensure that database goes to a consistent state. From there, either both A and B should be reset to 8 or both of them should be set to 16. Excuse me. Okay, so you want it to go from that point where you have this inconsistent state to either both A and B being set to 8 or both of them should be set to 16. Right? Any questions about this stuff? Okay. Right. So let's talk about the log. So log is an append-only file that contains log records. So you basically just keep adding stuff to it. And even though I talked about this notion of serializability, you could have multiple transactions that are run at the same time, and these log records of these multiple transactions are interleaved. So if you have a transaction that is touching A and B and another transaction that's updating C and D, you could have the log records of both of these transactions appearing in an interleaved manner. And after a system crashes, you will use the log to figure out what happened when the system crashed and which are the transactions that were partially executed, and so that you can undo the effect of the transactions that did not commit and redo some of the transactions that did commit. Okay, so if the transaction has committed but its changes are not reflected, you want to redo its effects. If a transaction did not commit, then you want to undo its effects. Right? You don't want a transaction that has partially updated some value its changes to be reflected on disk. So you want to undo the effects of those transactions. For the transaction that did commit but some of its changes are not reflected, you want to redo its changes. So I'll explain what I mean by that. So basically, there are three flavors of logging. The first is undo logging, the second is redo logging, and the third is undo redo logging. And we're not going to be covering this in class. We will be covering undo logging in class. This, I don't know. We'll see if there is time. Okay, so we'll definitely cover undo logging. Redo logging, we may or may not, depending on time. Okay, so let's talk about undo logging. So this is the three types of log records that can show up in an undo log. The first log record is a start record. So it says, hey, this transaction T has begun. Second type of log record is commit. So it says that this transaction T has committed. And the third is abort. So it says that this transaction T has aborted. And basically, if a transaction has been aborted, the transaction processing manager will ensure that no changes that T has made will appear on disk. Okay, so if on the other hand T has committed, then transaction processing manager will ensure that all of the changes that T made will appear on disk. Okay, so we talked about these three types of log records. The last type of log record is the value update record. So this log record has three parts. T is the indicator for the transaction or the transaction ID. X is a variable referring to the element. And V is the value of that element. Okay, so this log record says, hey, transaction T has updated element X and its old value is V. Okay, so the old value of X is V. And so this is a response to a write and not to an output. So remember that the output step is the last step where you're going and updating disk. This is a response to a write, which is something where you're modifying the main memory buffer but not yet modifying disk. The reason why this is a response to a write and not an output is because you want to record what has changed in memory because those are the changes that are going to be lost, right? If it has already been reflected on output, it's not as important. So you are recording what has changed in memory but may not have been changed on disk. Okay, so this is a response to something that you've changed in memory. So essentially what you're telling the system is, hey, you know what, I am going to modify X. So you're telling the system what is going to be overwritten. And the old value, just in case you need to recover from it, is V. Okay? All right. So there are two rules for undo logging, and it's super important that you guys understand these rules. The first rule is if a transaction modifies an element X, then this TXV entry must be written to the log before X is written to disk. Okay? So why is that? Why would we want to write this to the log before X is written to disk? Any idea? Yep.
Because if not, then we might write X to the disk, and then maybe the system would crash and we wouldn't have the log.
Exactly, right? So you need to record the value that you're overwriting before you modify the value on disk, because if you went ahead and modified the value on disk and then you crashed, you basically have no idea what you overwrote, right? So you need to record what you overwrote before you overwrite it, right? So you need to record what the old value was so that you can recover from a partially executed transaction, recover from a system crash. So that's perfectly right. Let's talk about the second rule. The second rule says if a transaction commits, then the commit T entry must be written to the log only after all of the changes by T are written to disk. So does this make sense? So why does this make sense? Yes?
If we were to put commit T in the log and then write to disk, then we could have some sort of failure between writing commit T and before we've written everything to disk. And we'd have the same problem with the first one.
Right. So you basically have this case where you've gone and so a commit record basically tells the log and the system that you're done with that transaction. Now, if you've gone and pushed the commit record or commit log record to the log before having actually committed, before having actually made the updates to disk, then you are in some sense deceiving the system by claiming to have completed the effects of a transaction even though you haven't, right? And so you could have these cases where you have, for instance, you've committed and then you've crashed after the commit, but you've not made the changes to disk, and therefore those changes will not be reflected on disk even though you want them to be reflected on disk. And so you can't, so, and if you're reading this log and you see, hey, this transaction has committed, you're going to avoid reprocessing that transaction. But unfortunately, in this case, the transaction's effects may not have been reflected on disk, right? And that's something you want to avoid. So let me try to state that again, and let me try to state that for both. Okay, so the first rule is you want to, if T modifies X, then the TXV entry must be written to the log before X is written to disk. So you want to record the old value before the new value replaces the old value permanently on disk. So this is an easier case. The second rule is if T commits, then commit T must be written to the log only after all the changes by T are written to disk. And here you want to ensure that all changes made by T have been reflected before T is allowed to commit. So in some sense here the outputs are done early before the commit happens. So You can think of a transaction as having three phases. The first phase where the transaction says, hey, I'm going to update all of these elements, just take a note of the early values of those elements. Then the transaction is going to go and make those modifications. Then finally, it's going to say, I'm done with everything, commit. Okay, so there are three phases. First phase is, let's call it declaration, and then update, and then commit. Okay, so here the transaction says, I'm going to go ahead and update these values. Here are the old values, just in case you need to recover from them, right? So that's via undo logging rule 1. Then all the good stuff in the transaction happens in the middle. It'll update some values, write them out to disk. And then finally, it says, hey, I've done everything I absolutely need to. Here's a commit statement. Right? So everything that the transaction is doing is happening before the commit statement happens. So when you see the commit statement, you know what, this transaction is done. It's not going to make any more updates. Yes? Okay. So, cool. So the rules say, like I said, you have the declaration part where you have log records indicating changed database elements, the changed database elements themselves, and then finally the commit log record. So let's walk through an example of how this may look for our toy example back there. So if you have this same scenario, you might have the log record with start transaction entry being flushed first, and then you've gone and made an update to A here, so you would add TA,8. 8 is the old value of A, so you've added this to the log, and then you've updated B here, so you've added this TB8, and here you have a flush log statement. You want, so the log also, once again, like blocks in memory, the log resides in memory up until this flush log statement, which pushes it to disk. Okay, so the flush log statement basically says, yeah, I know you've been recording all of this stuff in memory, but I really need you to push it to disk because I'm going to actually go ahead and make the modifications that I said I was going to make. So reflect the log records on disk before I can make those modifications, right? So here I basically said, look, the old values of A and B are 8. I need you to record that persistently or permanently on disk before I go ahead and update those values. So that's why I need to flush the log on disk, onto the disk, from memory onto the disk, before I actually do these output statements. Okay, so once I flush the log, I can go ahead and change the values on disk. So change it here, change it here. Now I'm done, right? So the transaction is finished making all of its updates. Now the transaction can commit. And then once again, you can flush the log to indicate that the commit has persisted, right? So the commit is permanent. I want to push it onto disk in order to indicate that if I were to recover from this, I will find that this transaction's effects are permanent. Okay, so given this sort of high-level idea of how this transaction would sort of indicate to the log what has changed and what has not changed, let's talk about how do you do recovery. So the recovery idea is basically for every transaction, you decide whether it's completed or not. So if you see a commit record, then you don't need to touch that transaction. It's done, right? And the reason why is because the commit record is always pushed onto disk after all of the transactions effects are reflected, right? So if you see a commit record on the log, then you know you don't need to touch that transaction. Similarly, if you see an abort record, it's analogous to the commit in that if you see an abort record, then all of the changes that are made by the transaction have been removed, right? There is nothing that needs to be done for that transaction. So once again, this transaction is complete, quote unquote complete. Okay, its effects are not reflected. Then the last case, which is the case that we have to worry about, is when you have a start transaction but you don't have a commit or an abort. This is a case that you need to focus on. And so the second part is that you need to undo all the modifications that are made by these incomplete transactions. Okay. So the recovery for an undo log proceeds as follows. You start by reading a log from the end, and then you have various cases. The first is if you see a commit record, then you mark the transaction as committed or completed. If you see an abort record, you mark the transaction as completed once again, because its changes you don't need to worry about. And then let's say you see a modification statement. If you see a modification statement and the transaction is not completed, then you need to revert its effects, right? So you've seen a transaction whose changes have not been reflected onto disk, so it's better to avoid all of those changes. So if it is not completed, then you change the value of element X to V. Otherwise, you ignore it, which means it's either a aborted or a committed transaction, so you can ignore it. And if you see a start transaction statement, once again, you can ignore that. Okay, so that's not really very important. Okay, so let's walk through how I would do recovery from this undo log. So it's really like, this is like, in some sense, this is reminiscent of forensic work. You basically have this log that's telling you what has happened before the system crashed. And you need to use the log to figure out what really went down, and you need to sort of recover from those issues. Okay, so the log has this. Okay, so you've recovered from a system crash. The log has these records. Start from the bottom, right? So you start from the bottom, and then you say, hey, this transaction updated value x2 from value v2, right? And transaction T2 has not yet committed. You've not yet seen a record for transaction T2. So what you're going to do is look at the value of x2. So let's say this is disk. And then whatever the value of x2 was, you're going to replace that with v2. Okay? So you're going to undo the effect of this transaction, which may have changed the value of x2 to something else. Then let's say you see a transaction T3 which updated the value of x3 from value v3. Once again, T3 has not committed. You've not seen a commit or an abort statement for T3, so you need to undo its effects. So what you would undo is, if you have a block or a tuple corresponding to x3, you'll update its value to v3. Okay? And separately, you're going to have a place where you will record the committed transactions. So we see a commit statement corresponding to T5. So what I need to do is to record that T5 has committed. Okay? And this will come in handy later. Then I see an update corresponding to T4. T4 once again has not committed, so I need to undo its effects. So T4 updated X4 and from value V4 to something else. So I'm going to update X4 back to V4. Okay, essentially I'm undoing the effects of T4. Then I get to this statement, which is corresponding to T5. Since I've seen a commit for T5, T5 is part of the committed transactions, I don't really need to worry about this log record, because this log record has already been, its effects have been felt on disk. I don't need to worry about it. Right? Any questions about this? Okay. So then I see transaction T1, which updated the value of X1 from V1. So I need to undo its effects. So I'm going to undo X1 back to V1. Okay, so, and then the start transactions I don't need to worry about. and then I keep going, and I have to undo basically everything that I have not seen a commit or a abort for. So here once again I see T6 which is not committed or aborted, and therefore I need to undo its effect. So I would update X6 to V6. Yes? So, I mean, you don't really need to do anything special with the start transactions, at least in this particular context, because it doesn't help you. I mean, the set of committed transactions don't change. You don't need to make any updates on disk. It's not important. Basically, you can just ignore those records. Okay? All right. So, I guess I'm walking through the steps again here, so I'll just do that. So T2 will write V2 to X2 on disk. For T3, I need to undo its effect, so I'm going to write V3 to X3 on disk. I mark T5 as completed for this commit statement. I will then write V4 to X4 on disk. I will skip this, right? I can skip this guy because I know T5 is committed. I write V1 to X1 on disk. And then I keep going, I write V6 to X6 on disk. Okay, so the reason why we are able to do this is because all of these undo commands are idempotent, right? So if you perform them a second time, no harm is done, right? So let's say a transaction wanted to update its value of A, element A, from 8 to 16, right? And let's say you've recorded on the log that A wanted to update, let me try to do that again. So let's say transaction T wanted to update the value of A from 8 to 16. You've recorded on the log that T wanted to update A with old value 8. Okay? Now let's say T actually went ahead and did update the value of A to 16. So when you process this log record and T did not commit, then you can change this value of 16 to 8, right? But on the other hand, if T had not yet updated the value on A of 8 to 16 and it was still 8, even if you change this value from 8 to 8, it's still going to give you the same thing. So basically, these undo commands are idempotent, right? So if you do them a second time, if you undo something that was already okay to begin with, no harm is done, right? So, and also if there's a system crash during recovery, you can simply restart recovery from crash. So that's another side effect of this. So since these undo commands are idempotent, I mean, in some sense, if you do it a second time, it doesn't cause any harm. So you can simply process them once again. So if you have a system crash during a system recovery, you can once again process from the bottom of the log, and you will end up in a consistent state. Okay, so let's see what happens in our toy example. So you had the log consisting of these 4 elements outputted at various times, and let's consider various scenarios, right? So if you have a crash here at step 1, here you have A is equal to 8 and B is equal to 8 on disk. At this point, you have A is equal to 16, B is equal to 8. At this point, you have A is equal to 16, B is equal to 16. And at this point, you also have A is equal to 16, B is equal to 16. Now, at crashes at this point, and this point, you will not see the commit log on disk. Because you will not see the commit log on disk, you are going to undo the effects of the transaction T. So you will rewind to 8 and 8 for A and B. This is true even though you may have been in this step, in step 3, where you've updated the values of A and B both to 16. So you're in a good shape, and you should ideally want the transaction to say, hey, I'm done. But simply because you did not see the commit log on disk, you're going to undo the effects of this transaction, and you're going to rewind it back to A is equal to 8 and B is equal to 8. Okay, and similarly you're going to do so for this stage and for this stage. You're going to rewind it to A is equal to 8, B is equal to 8. For this stage, after the commit, you don't need to rewind it because it is committed. Okay, so it is committed, therefore you don't need to rewind it. All right. So one question here is, when do we stop reading the log? When do we say, hey, look, I'm done? Unfortunately, we can't stop reading the log until we reach the beginning of the log file. So this is one major drawback of this recovery scheme. So let's say, for instance, I have been recording transactions since 2005. I may have a log record that goes back to 2005. This could be several terabytes long, right? So I don't want to read this log file all the way back to 2005, right? So I don't want to do this. So a better idea is to use checkpointing that allows us to stop the processing of the log at some point in order to say, I don't need to look back beyond this point. Okay, so the checkpoint allows you to say, look, this is the point of the log up until which I need to read. Beyond this point, I don't need to worry about it. So that's the idea of checkpointing. So let me get into checkpointing a little bit in the next set of slides. Any questions about this stuff so far? Yes? The what? Last failure time. So the thing is, you could have a transaction that lasts a very, very long time, right? So you could have a transaction that, for instance, lasts several days. You have a failure at, let's say, today, but your transaction started 3 days ago. You need to go back to the log point where this transaction sort of started in order to undo all of its effects. Right? So you can't avoid processing the log file, and by the same argument, you could have a transaction that's lasted very, very long, and you need to undo all of its effects. So in the worst possible scenario, if you have a transaction that started in 2005, it's been slowly updating various things, I need to undo all of its effects. Right? Any other questions about this stuff? Okay, so let me switch to checkpointing. So what would be a good strategy for checkpointing? Maybe I'll ask you folks first. So I want to avoid reading to the start of the log file. How do I prevent doing that? What would be a good strategy to avoid reading till the start of the log file? Yep.
Maybe put in a checkpoint every time you've reached a moment where every transaction that's been started has been committed.
That's a great idea. So what he said was, why don't you add a checkpoint at a point where every transaction that has started has committed? So that's a great idea. So that's essentially the idea behind the first strategy. So the first strategy says, I'm going to wait until everything that has started has committed. I'm not going to admit any new transactions. And then I can add a checkpoint. If I've added a checkpoint, that means that I don't need to worry about anything above this. I only need to worry about everything below. Right? So that's essentially the idea that he said. And that makes total sense. So for instance, I could say, look, I'm not admitting anything new. I just need to wait until these transactions are completed. And then once they are completed, I will say checkpoint. I'm done with them. So everything above that point in the log file is essentially not necessary. So that is the first strategy. So the first strategy will stop accepting new transactions, wait until the current transactions complete, and then flush the log to disk. And then you write the checkpoint log, once again flush, and then you resume transactions. Okay, so you have these phases. So you, at this point, let's say you decide to checkpoint, you wait until the existing transactions finish in this period, and then you flush all of their log records to disk. Here you write a checkpoint log record and then you flush it to disk, and then here you're done, right? So basically everything in this part is done and checkpointed, so you don't need to worry about it. And then from this point on you can accept new transactions, and then you need to only worry about these transactions after that. So then basically during recovery you can stop at the first checkpoint log record that you encounter when you're reading the log from the bottom up. So in this particular case you have transactions T2, T3, T4 and T5, and then you have a checkpoint here, which means that everything else that has started before this has all completed at this checkpoint log record. So you don't need to go above that. Okay? So that's essentially this idea. So you sort of undo the effects of everything up until this checkpoint, and then you stop. Okay, so let me walk through how I would do this once again so that you get the intuition. In fact, this is the exact same example, so maybe I don't need to do that. So here you would, so maybe I'll ask you folks. So which of these commands would I, which of these, or rather what would I do in each of these cases, right? So here I'm going to undo the effect of this transaction because it's not committed. Would I undo the effect of the next one? Yes. What would I do for this statement? So T5 has committed. So I need to record somewhere that T5 has committed, because if I see any other updates made by T5, I would need to ignore those updates. So I will have a special place, let's say committed transactions, where I will update that T5 has committed. Okay? Then do I undo the effect of this? Yes. Do I undo the effect of T5? You can skip it, right? Because T5 is committed, so I don't need to worry about this. T1, I will need to undo it. And these are all start transaction statements, so I don't need to worry about that. Then now I've hit the checkpoint, so I'm done, right? Okay, so what's a downside with this approach? There's one obvious downside with this checkpointing approach. What's the downside? Yes? Say that again? People keep starting. So yes, so intuitively you have the right idea. So basically you're saying that there are transactions that are happening all the time and you don't have a place to stop. In some sense, in this strategy, what you're saying is I'm going to wait until all of the current transactions are finished, and then only will I let new transactions to come in. But if, like you said, if there are transactions that are happening all the time, then I'm preventing those transactions from even starting, right? I don't like that, right? So would you like a banking software that says, sorry, we are not accepting transactions between midnight and 1 a.m.? You don't want that to happen, right? You don't want your software to be unavailable at any time. So the new strategy that I'm going to introduce is what is known as a non-quiescent checkpointing. So if you're not familiar with the word quiescent, it basically means not malleable, or quiescent is sort of agreeing to. It's kind of, does anyone have a good definition for the word quiescent? Quiescent is basically sort of deferring, something that defers to, something that's more malleable, that's more, is that the meaning? Okay, let me look it up because I have a minute. Okay. Such a good use of time. I was incorrect. Okay, so quiescent is in a state or period of inactivity or dormancy. So I was incorrect there. So this is basically saying I don't want this system to be inactive or dormant at any time, which makes a lot more sense than the definition that I was spewing on you guys. So a non-quiescent checkpointing basically says it does not have this period of dormancy. It is going to be active at all points. So the non-quiescent checkpointing basically would not prevent transactions from starting. So it will allow transactions from starting, but it will write a start checkpoint record with all of the active transactions at that point. It will continue normal operations. So new transactions may start, but when all of transactions T1 to Tk have completed and flushed, you will write an end checkpoint statement. Okay, does this make sense? So you write, you don't stop taking transactions. You do continuously take in transactions. What you write is you say, hey, at this point, all of these transactions were active. T1 through Tk were active. Then once you've written that out, you may have new transactions that start, Tk plus 1, Tk plus 2, and so on. And then when all of T1 through Tk have completed and it's their effects reflected on disk, then I will say end checkpoint. So it's not, unlike the previous case where there is one period of checkpoint which says, okay, I draw a line in the sand, everything above it has finished, everything below it is unrelated to stuff that's above. Here there is a period of sort of ambiguity. So I draw a line by saying, hey, these are the transactions that are still active at this point. And then I draw a second line that say that, you know what, all of those that were active, they've all completed by the second line that I've drawn. Now that helps me because when I encounter this end checkpoint statement, I know that the transactions that were active beyond the start checkpoint statement, I don't need to worry about. Right? So I only need to worry about everything that happened in between. Everything before that start checkpoint statement, I don't need to worry about. Okay, so I'll tell you what to do with this in the next class. Any questions about this stuff so far? Okay. All right, see you on Wednesday.